Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on utility systems which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the basic components of a steam system, describe raw water and fire water systems, describe boiler feed water treatment, describe the basic components of a cooling water system, describe the basic components of an air system, describe the basic components of a nitrogen system, describe the basic components of a gas system, describe the basic components of an electrical system, describe the basic components of steam systems and traps, describe the basic components of an industrial sewer system, describe the key elements of a process refrigeration system, describe a relief and flare system. Before starting the course, let us have a look at key terms. Anions are negatively charged ions. Blowdown is the process by which water is removed from the boiler system. British Thermal Unit, BTU, is Energy Measurement Unit. 1 BTU is the energy needed to raise 1 pound of water 1 degree Fahrenheit. Carryover is contamination of steam with boiler water solids. Cations are positively charged ions. Flare is a device to safely burn excess hydrocarbon vapor. Flare header is a pipe that connects the plant to the flare. Flocculation is the bridging together of coagulated particles. Knockout drum is a tank located between a flare header and the flare, used to separate liquid hydrocarbons from vapor. Latent heat is the heat that cannot be measured, the heat required to change a liquid to vapor, latent heat of evaporation, or vapor to a liquid, latent heat of condensation. SHP is super high pressure steam that operates between 1000 and 1200 psig. Introduction to process systems. Chemical plants and refineries include unique combinations of equipment and systems that are used to separate materials into pure or relatively pure products. Examples of process systems include reactions, distillation, absorbing or stripping, adsorption or drying, crystallization, evaporation, extrusion, extraction, filtering, screening, and utility systems. Plant utility systems typically include steam generation, compressed air and gases, water treatment, and cooling tower operations. Steam generation systems. A steam system is a complex arrangement of equipment and piping that works together to produce and circulate steam at a variety of pressures and temperatures. Because steam is used in so many industrial applications, most chemical plants and refineries have their own steam generation facilities. In a closed steam system, a condensate return header is used to remove slugs of water or condensate from the live steam line. This treated water collects in low points in the system, where devices called steam traps direct flow back toward the boiler. A vessel called a deaerator is used to collect fluid from the condensate return header. The deaerator is designed to remove excess air from the system. Demineralized makeup water is often added to the deaerator. The cooled condensate is fed back into the boiler, where it is changed into steam. A typical steam system will include the following equipment: boiler, fire tube or water tube. Steam header system, low, medium, and high pressure. Condensate return system, steam traps, valves, piping, pumps, deaerators system. Steam systems can include super high pressure, SHP, steam generation and distribution, high pressure, HP, steam, medium pressure, MP, steam, and low pressure, LP, steam. Super high pressure, 1000 to 1200 psig. Super high pressure steam is generated in fire tube or water tube boilers. This allows the boiler plant operator to deliver steam to remote locations of the plant. However, many process systems are not designed to operate at super high pressures. In this situation, the pressure is reduced to the correct operating condition. A relationship exists between the pressure and temperature of the steam. The higher the pressure, the higher the temperature of the steam. Process technicians use steam tables to identify the temperature of steam at a given pressure. The SHP steam is generated by a boiler and is supplied to the SHP steam header. The typical pressure of the SHP steam is 1000 to 1200 psig. SHP steam is supplied to turbines, which drive compressors. In order to control the pressure in the high-pressure steam header and to transfer excess amount of high-pressure steam to the high-pressure steam header, a letdown, pressure-reducing, station is provided between the SHP steam header and HP steam header. High-pressure steam system, 400 to 800 psig. HP steam is supplied as required by lowering the pressure from the SHP header. High-pressure steam extracted from steam turbine drives can be used to feed the HP steam header. HP steam may be imported from other units into the high-pressure steam header to maintain overall steam balance. Extraction steam and imported steam flows are regulated to maintain the header pressure at 400 to 800 psig. The pressure of the imported steam supplied through a pressure control valve is slightly higher than HP header pressure. In order to maintain pressure and steam balance in the medium pressure steam header, a letdown station is provided between the HP steam header and MP steam header. Medium pressure steam system, 180 to 200 psig. Nominal steam pressure in the MP steam header is 180 psig. Medium pressure steam is supplied by lowering the pressure from the high pressure header or by extracting exhaust steam from steam turbine operations. As high pressure steam enters a turbine, it is partially converted to useful mechanical energy. Non-condensing operations utilize the exhaust steam in operations where lower pressures are required. MP steam is supplied partially by exhaust from small back pressure turbines and extraction steam from larger turbines. In case of insufficient supply from the above sources, the letdown station between the HP and MP headers makes up the balance of steam required at the MP header. Low pressure steam, 50 to 60 psig. LP steam is supplied by lowering the pressure from the MP header, or by extraction from a steam turbine continuous blowdown drum. Nominal steam pressure in the low pressure header is 50 psig. Steam to the LP steam header may be supplied from the exhaust of steam turbine driven pumps. The letdown station between the MP header and the LP header maintains the balance of steam in the LP header. An automatic pressure-controlled dump system with silencers is provided to dump excessive steam from the LP header to the atmosphere during plant operation upset conditions. Condensate recovery. The condensate recovery system is separated into clean and suspect, dirty, condensate sections. Clean condensate is routed to the deaerator. Suspect condensate is collected from steam users where the process side pressure is higher than the steam pressure. This condensate is considered to be suspect because a mechanical failure, such as tube leakage or failure, could cause contamination, and the reuse of contaminated condensate could seriously damage the steam generators and turbines. Suspect condensate collected in a drum is closely monitored for hydrocarbon contamination. Depending upon the results of analysis, the condensate is pumped through a carbon filter and then routed to the deaerator. Raw water and fire water systems. A storage reservoir, supplied from municipal sources or local rivers and lakes, normally supplies the plant systems that require raw water, RW, which is used for all purposes throughout the plant, and fire water, FW, which is used only in specific units such as boilers, which usually must be treated for purity. Raw water is supplied to the units in the plant by pumps. All pumps can be remotely started from a utilities unit control service. Normally, 1 or 2 pumps are in operation to maintain 125 to 150 psig pressure on the RW system. All raw water lines are located above grade. Plants use raw water in utility station water hoses, process unit fire water, FW, hose reels, the cooling water supply, the supply to the fire water system, and boiler feed water makeup. fire water is supplied to the plant by pumps, which must be capable of continuing to run if power to the plant is lost. These pumps are typically diesel-driven to ensure operation if electric power is lost. The FW system pressure can be supported by cross-connecting from the raw water system. Note that operations at some plants can differ greatly from those described in this course. The fire water pumps are instrumented to start automatically when the fire water system pressure declines below 110 psig. The first backup pump starts at 110 psig, the second diesel-driven pump starts at 100 psig, the third diesel-driven pump starts when the system pressure drops to 90 psig. Some plants operate at a fire water system pressure as high as 300 psig. These pumps can also be remotely started from the Utilities Unit Control Center. All lines in the FW system are underground, with a minimum of 2 feet of cover. Each process unit has a loop system, which supplies FW to the unit. Loop isolation valves are installed in order to isolate any leaks or broken lines in the loop. Fire hydrants are located on road shoulders on all sides of the units and inside the unit. Deluge systems on storage vessels are also supplied from the FW systems. Boiler feed water treatment. Boiler feed water treatment is the process by which suspended and dissolved solids are removed from the waste used in a plant. Clean condensate and demineralized makeup water are deaerated in order to supply boiler feed water, BFW, to multiple BFW pumps. 2 or 3 pumps are used in the pump-around operation. The primary pump typically has 1 or 2 backup pumps that are placed in standby mode. It is essential that all impurities be removed, otherwise, harmful scales or excessive corrosion will occur in the boilers. High concentrations of dissolved solids in boiler water will cause foaming of the water within the boiler. Foaming produces carryover of impurities in the steam, resulting in deposits on the turbine wheels. Impurities in the water. The impurities that are present in water supplies can be divided into suspended and dissolved solids. Suspended solids are those that do not dissolve in water and that can be removed by filtration. Examples of suspended solids are mud, clay, and silt. Dissolved solids are those that are naturally dissolved in water and, therefore, cannot be removed by filtration. Examples of dissolved solids are sodium chloride, common table salt, calcium carbonate, limestone, silica, sand, calcium sulfate, gypsum, magnesium sulfate, Epsom salts, magnesium carbonate, dolomite, hydrated sodium sulfate, Glauber's salt, aluminum, iron, manganese, fluorides, and other trace substances. Impurities must be removed from water before it can be used in industrial applications. This table shows the standard for boiler operation established by the American Boiler Manufacturers Association, ABMA. Physical properties of water. Water is one of the most abundant resources found on Earth. In its purest form, water is colorless, odorless, and tasteless. It is the only inorganic substance that occurs in all 3 states in the Earth's temperature range: ice, solid, steam, gas, and water, liquid. A molecule of water has 2 hydrogen atoms and 1 oxygen atom. Its chemical formula is H2O. Water boils at 212 degrees Fahrenheit or 100 degrees Celsius at atmospheric pressure. Pressure increases cause the boiling point to rise, and pressure decreases cause it to fall. For example, at a pressure of 200 psig, water has to be heated to 388 degrees Fahrenheit before it will boil. When atmospheric pressure is removed, water will boil at temperatures as low as 35 degrees to 40 degrees Fahrenheit. At 3,200 psig, water approaches the critical pressure, at which water is converted to steam without a volume change. Processing units for boiler operation and a wide variety of other applications use steam. It takes 1 British thermal unit, BTU, to raise the temperature of 1 pound of water 1 degree Fahrenheit. It takes 970 BTU to change 1 pound of water to steam. This heat energy is stored in the steam and will not be released until the steam begins to cool and condense. Heat stored in steam is often called the latent heat of vaporization. 1 pound of boiler feed water at 72 degrees or 22.2 degrees Celsius requires 140 BTU to reach 212 degrees Fahrenheit or 100 degrees Celsius and an additional 970 BTU to change to steam. A total of 1,110 BTU is stored in the steam. In the reverse process, the energy released when steam changes to water is the latent heat of condensation. Local water reservoirs and storage systems have a wide range of natural water quality, including various amounts of impurities. At higher temperatures, the dissolving nature of water is enhanced, so the amount of dissolved solids may be increased. Water hardness is associated with the presence of calcium and magnesium compounds. Salt water varies from fresh water in the salt mineral content of the water. Salt water contains 300 pounds of salt for every 1,000 pounds of water. As boiler feed water temperature increases, impurities precipitate, fall out, and adhere to the hot metal surfaces of the boiler, forming scale. Typically, dissolved bicarbonates of calcium and magnesium break down and form insoluble carbonates. Deposits in a boiler are composed of a variety of compounds, including calcium carbonate, calcium phosphate, sulfate or silicate, magnesium hydroxide, iron, copper oxides, and silica. Phosphate deposits are soft brown or gray and can easily be removed. Carbonate deposits are granular and porous. Sulfate deposits have a crystallized structure that forms a dense and very hard deposit. Silica deposits are very hard, with a fine crystallized structure that resembles porcelain. Iron deposits are characterized by a dark brown color. The primary problem associated with deposits is tube failure. Corrosion. The process of corrosion is a complex electrochemical reaction that can attack a large area or a small pinpoint area. Corrosion in a boiler is typically associated with the reaction of oxygen with the metal. However, pH, a measure of acidity, stress, chemical compounds, and other factors can contribute to corrosion. Corrosion may occur when the boiler or boiler feed water has excess acidity or alkalinity, high levels of oxygen and carbon dioxide, high temperature, stress, or high levels of ammonia or sulfur-bearing gases. Corrosion fatigue occurs when thermal warp, caused by rapid heating or cooling, affects a weakened area, or it may be caused by cracks created internally from the action of applied cyclic stresses. Caustic cracking is characterized by metal stress, embrittlement, caustic water, presence of silica, and a small leak that focuses stress on a small area. Corrosion prevention is characterized by maintaining pH levels in boiler feed water, removing dissolved oxygen from water, using chemical treatments, and following established out-of-service and blowdown procedures. Poor water quality will produce poor quality steam that results in boiler water foaming, which produces carryover or contamination of steam with boiler water solids. Deposits of solids can damage the steam system. The primary causes of boiler water carryover are foaming that is froth carried out with steam, aqua globe ejection that is water spray carried out, load changes or priming, like uncapping a bottle of soda, and steam contamination that is leakage of water. Avoiding high water levels in boiler load changes and maintaining proper concentration of solids prevent carryover. Coagulation and flocculation. Coagulation neutralizes the negative charges of suspended solids, thereby allowing them to clump together and settle out. Flocculation is a term used to describe the bridging together of coagulated particles, that is, floc. Common coagulants include aluminum and iron salts. Chemical names for these coagulants include ferric sulfate, ferric chloride, aluminum sulfate or alum, and sodium aluminate. Aluminum and iron have 3 positive charges that counter the negative charges of the suspended solids. Coagulants form a floc net that collects suspended material. Chemical precipitation. Chemical precipitation uses a chemical to react with dissolved minerals in feed water to form a solid precipitate that drops harmlessly out of solution. Lime soda is frequently used as a water softening agent. Calcium hydroxide reacts with soluble calcium and magnesium bicarbonates to form a solid precipitate. These reactions are illustrated by the following equations shown in picture. Settling and filtration are used to remove the sludge or solid precipitate. Soda ash is also used in the water softening process. It is used to reduce sulfate hardness. Modern manufacturers use two approaches when adding lime soda for water softening: batch and continuous. Batch uses only one tank. Continuous softening uses multiple compartmented tanks, continuous additive addition equipment, and retention time for chemical reaction, sludge removal device, and clear water draw-off. Ion exchange process, demineralization. Ion exchange resins are used to remove electrically charged particles or ions from water. When minerals are dissolved in water, they form ions. Ionic resins come in two types: anion, negatively charged ions, and cation, positively charged ions. Anion resins react with negatively charged ions such as sulfate. Cation resins react with positively charged ions such as calcium ions and magnesium ions. Ion resins resemble small beads and are placed in tanks that raw water is passed through. Resin beds are usually several feet thick. Demineralization is a process that passes raw water through both anion and cation exchange resins. Effluent from this process is essentially pure water. De-aeration. A deaerator is a device used to remove air from water. The deaerator is typically located at the end of the condensate return header and is used as the primary boiler feed source. Dissolved oxygen is a serious problem because it leads to boiler system corrosion. The deaerator is designed to remove dissolved oxygen by heating the water with steam. Dissolved oxygen passes out the vent with the steam. Deaerators come in two basic designs: spray and tray. Spray deaerators inject steam directly into the water. In the tray design, steam enters at the bottom and water enters at the top. Water drops over a series of sieve trays that provides good contact between liquid and heated vapor. Water treatment in boiler. Water treatment is classified as external or internal. External treatment takes place before raw water enters the boiler. Internal water treatment complements the external process and helps protect the internal components of the boiler system. In some systems, external treatment is limited. The primary location for water treatment is at the boiler. Common tests on boiler feed water include pH and the presence of particulate matter, measured in ppm, iron, oil, and silica. Blowdown. Blowdown is a term used to describe the process in which water is removed from the boiler system. As suspended solids concentrate in the water, chemical treatment reaches a point at which it is no longer effective. Removal of a portion of the treated water is necessary. Blowdown depends upon the amount of suspended solids the boiler can handle. It is not unusual for blowdown to equal 5% to 10% of the total capacity. Blowdown is controlled through an instrument designed to measure the electric conductivity of the water. Blowdown ports are typically located on the bottom of the boiler so accumulated sludge can be removed. This table lists common boiler water problems. Cooling water system. The cooling water (CW) system is used for cooling the various pieces of equipment in the facility in a closed cooling system. The cooling water system is divided into two complementary circuits. One CW circuit operates on a once-through basis, the other allows the reuse of water to cool a second train after use for cooling the first train. The cooling water system is designed for a supply temperature of 90 degrees Fahrenheit or 32.2 degrees Celsius and a maximum return temperature of 120 degrees Fahrenheit or 48.88 degrees Celsius. A cascade arrangement is used to minimize the amount of circulation water while maintaining the design temperature rise. This cascade arrangement takes advantage of process users that are cool enough to maintain a temperature rise between 5 degrees or minus 15 degrees Celsius and 10 degrees Fahrenheit or minus 12.2 degrees Celsius. The cooling water is supplied from the cooling tower to the users by cooling water circulation pumps. Cooling water pumps are typically centrifugal and vertically mounted. The driver can be an electric motor or steam turbine. Makeup water to the cooling tower is supplied from the raw water system. Raw water storage must have sufficient capacity to withstand interruptions in the water supply. The recirculating cooling water concentration ratio is designed for a minimum of 5 cycles and is controlled by blowdown. Continuous blowdown is used to prevent buildup of dissolved components. The cycles of concentration are controlled at the blowdown valve on the basis of the recirculating water conductivity. Side stream filters may be used to remove airborne solids such as dust and sand and contaminants introduced via the cooling tower makeup water such as silt, organic matter, and waterborne organisms. Each filter is sized to handle the full flow while one filter is backwashing or out of service. The side stream filters operate automatically under gravity flow and are of the self-contained backwash type. The cooling water chemical feed system consists of a non-chromate-based corrosion inhibitor, a dispersant or anti-scalant, and chlorine for the control of microbiology fouling. Air and nitrogen systems. Air systems. Utility and instrument air are both supplied from centrally located air compressors. Drivers for the compressors are arranged so that the loss of power or steam will not interrupt the supply of critical instrument air. Some plants have additional diesel-driven compressors in case the two utilities are not available at the same time. Normal plant demand may require only 1 or 2 air compressors to be in operation. The air compressors are set up to produce approximately 125 psi air pressure into the system. Because the instrument air (IA) system is the more critical system, pressure is controlled to 100 to 105 psi. Utility air (UA) has no pressure control. Plant air systems. A central utilities unit supplies utility air for the entire plant. Free water is removed at a separator drum that is located off the air compressor discharge but is not dried. Utility air is used for unit hose stations, general use, air-driven tools, and Deco King unit furnaces. The largest use of utility air is in the Deco King unit furnace, which is operated intermittently. Usually, an extra air compressor is put online during these periods. Utility air should never be used for unplugging lines or sewers or for removing liquid hydrocarbons from trucks or vessels because of the hazard of creating combustible mixtures. Instrument air system. Instrument air is dried to approximately 250 degrees Fahrenheit or 245.55 degrees Celsius dew point with activated alumina desiccant. Instrument air system pressure is protected against low pressure as a result of excessive utility air usage by an upstream pressure controller in the utility air system. This control valve will close off if the instrument air header pressure falls below 95 psi. It is important to maintain the instrument air system pressure at its normal controlled pressure of 105 psi because some control valve actuators begin to malfunction when the pressure drops below 60 psi. At some locations, the plant instrument air system is protected against pressure failure by a tie-in to the nitrogen N2 system. Because of safety concerns, nitrogen is admitted into the instrument air system only during an emergency. An alarm or alert system is in place to warn all unit personnel whenever nitrogen is added to the instrument air header. Nitrogen systems. Nitrogen gas is usually generated in the plant or purchased from a supply company. If purchased, it is usually delivered by high-pressure pipeline. Pipeline pressures run from 300 to 600 psi. The supplier may own and operate the meter station, which forms the billing basis for the purchase of nitrogen. High-pressure nitrogen is delivered to the individual units in a plant. the pressure is reduced at each unit to the desired working pressure, which is usually 120 to 150 psig. Nitrogen is used primarily as an inert gas for blanketing vessels and lines or for conveying combustible materials, and sometimes as a backup for instrument air. Nitrogen hose connections are located at utility stations in the process units. These connections are used for nitrogen only and are different from the connections used for air, water, or steam. The nitrogen connections, natural standard coupling, are welded to prevent them from being changed to other types of fittings, namely air or water. Gas systems. Most industrial manufacturers purchase natural gas (NG) from suppliers. A high-pressure pipeline generally delivers gas to the plant. A pressure letdown station located near one of the plant entrances meters flows to the plant. The letdown station consists of multiple control valves, 2 of which are normally in service for backup. Additional valves are provided for peak loads such as unit startups. The letdown/meter control valve is in operation at all times. A second valve opens when the flow rate is high and closes at low flow rates, thereby making possible more accurate metering of the gas flow. The plant natural gas distribution header normally runs around 200 to 250 psig. Each process unit has its own pressure control station that usually maintains the unit pressure between 60 and 100 psig. Natural gas is used to supplement the fuel gas produced at a unit in order to meet furnace and boiler demands. Natural gas is also used as a purge medium in unit startup and shutdown. Fuel gas generally consists of plant-produced process gas that is augmented with purchased natural gas to satisfy the unit's energy demand. Fuel gas required is typically produced internally during normal unit operations. During a startup mode or emergency mode, where no internal fuel gas is available, gas is imported. The imported gas is measured in a meter station before entering the unit. During normal operation, any excess fuel gas produced is exported by a compressor system. Electrical systems. The power received from electric supply companies is generally at voltage levels of 100 to 160 kV. At many plants, this is transformed down to 13.8 kV for distribution within the plant. At the units, the 13.8 kV is stepped down to 4,160 V for use on large motors, 200 to 10,000 horsepower. The 13.8 kV is also transformed to 480 V, the most common voltage in many plants, and finally to 240 V and 120 V for heating, lighting, and fractional horsepower motors. Motors. Most of the motors in the plant are the 3-phase induction type. Each of the pairs of poles is wound with one of the phases of the AC supply. The effect of this winding is to produce a rotating magnetic field. This field, in effect, pulls the rotor behind it, thus imparting mechanical energy to the machine. The induction motor always rotates slightly slower than the magnetic field. Some motors are made to rotate at the same speed as the magnetic field. These are called synchronous motors. Further discussion is beyond the scope of this book, except to say that synchronous motors are generally more economical than induction motors for very large applications. Motor protection. In addition to mechanical energy, electric energy can also be converted to heat. This is what happens in a toaster or an electric stove. The amount of heat produced is proportional to the product of the current squared or I squared times the resistance, Ri square R. The household fuse operates on the principle that it is the weakest link in the circuit. When the current gets large enough to nearly overload the circuit, the fuse burns out and interrupts the circuit. Large-scale motors have the same type of protection, generally called circuit breakers. These breakers, located in the Motor Control Center, MCC, actually afford 2 types of protection. One type protects against the instantaneous very large overload, such as might occur if a short circuit develops in the system. The other is a thermal overload that protects against continuous operation at a high motor loading. Either of these devices can shut down a motor. Knowing which of these devices was activated can be a clue as to what is causing the problem. Voltage measurement, voltmeters. Voltmeters are connected in parallel with wires in an electric circuit. Normally, we are not concerned with the internal construction of voltmeters and do not see anything except the dial. Actual volts are indicated on the dial, and no conversions or calculations are necessary. Current measurement, ammeters. Ammeters are similar to voltmeters, except that they are connected directly in one line of the electric circuit. Ammeter readings are read directly from the face of the meter. Backup power systems. Backup power systems ensure continuous power supply to critical equipment and instruments. In addition to the normal power, an emergency diesel engine generator and an automatic transfer switch provide an alternate source of power. When normal power is lost, the transfer switch delivers backup power from the emergency diesel-driven generator. The critical instrument systems are supplied with power through an uninterruptible power system, UPS. This system contains batteries, a battery charger, inverter, static transfer switch, and manual bypass switch. This backup system ensures that there will be no interruptions to alarms, computer control systems, and all other instrument systems. Many plants generate power in addition to that purchased. This is generally at a voltage level of the supplier or at the highest transformed plant voltage level. Steam systems. Steam has been used as a source of heat and a conveyor of energy since the Industrial Revolution. It is produced by boiling water, and its temperature or heat value can be easily determined because it generally corresponds to the pressure in the system shown in table. Steam carries large amounts of energy in small mass flow rates. The energy of steam is readily transformed into mechanical or heat energy upon condensation. As we mentioned earlier in this video, steam systems can include super high pressure steam generation and distribution, high pressure steam import, medium pressure steam, and low pressure steam. SHP steam is generated by boiler or furnaces and is supplied to the SHP steam header. The pressure of the SHP steam is 1000 to 1200 psig. Steam is distributed throughout the plant by progressive letdown from preceding headers and extraction from turbines. High-pressure steam flows are regulated to maintain the header pressure at 400 to 800 psig. The steam pressure in the MP steam header is 180 to 200 psig. The steam pressure in the LP header is 50 psig. Steam traps. Two types of heat are present in steam: sensible and latent. Sensible heat is heat that can be sensed with a thermometer. Latent heat cannot be sensed, but it is still present and is given off when steam condenses. A steam trap stops or traps the steam until it gives up its latent heat and condenses. The steam trap then allows the condensate to discharge and return to a boiler, where it is reheated into steam. Without a steam trap, the steam would not give off its latent heat, and the efficiency of the heat transfer in the heat exchanger would be greatly reduced. This reduction in efficiency can be translated into increased energy costs. Avoiding these increased costs is the primary reason steam traps are used. Steam traps are also used to remove air and dirt from steam systems. Trapped air is especially dangerous in steam systems because oxygen in the air can oxidize steam lines. Over an extended period of time, this oxidation process will eat through the steam pipes and create severe steam leaks. All steam traps are designed to distinguish between steam and condensate. To be effective, a trap must stop or trap steam and release condensate. The variety of differences between the physical properties of steam and of condensate has led to a variety of approaches in steam trap design. Some traps, for instance, are designed to distinguish between the density of steam and of condensate. Other traps are designed to distinguish between the temperature of steam and of condensate. Still others recognize pressure differences between steam and condensate. three commonly used types of steam traps are the inverted bucket, impulse, disc or float, and thermostatic, bellows, traps. Steam traps are sometimes considered a special type of check valve. They permit flow in one direction only. In addition, they permit the flow of only certain fluids. The basic purpose of a steam trap is to allow hot water or steam condensate to pass while holding back steam. Steam traps are sometimes used on steam-heated process equipment to remove large amounts of condensate. Another use is on steam tracing and jacketing. It is important for a trap to work properly. If it does not allow collected condensate to pass, steam flow will stop. When steam flow stops, the temperature is no longer maintained on the process equipment or the tracing. If the trap does not close, live steam will continually pass through the trap without being condensed. Depending on the details of the condensate collection system, the passage of uncondensed steam can be very wasteful in terms of heat energy loss and can cause thermal shock in pipes and systems. Bucket steam traps are used on drip legs and tracing, with moderate heat loads. Operating pressure differential should be specified. Traps must be primed to function and will pass live steam when dry. Bucket steam traps will fail to open. They should not be used in intermittent service or used where steam is superheated. They can be used in continuous winter service, but the trap must be protected from freezing. Impulse traps are used on steam tracers and drip legs. They do not operate at pressures above 300 psig or below 15 psig. Impulse traps will fail to open. They are self-draining when installed in the vertical or horizontal position with the cap on the side. Thermostatic, bellows, traps are used in intermittent and 5 psig or lower service. An 18-inch minimum vertical leg is required for horizontal or vertical installation. Bellows traps are self-draining when the outlet is vertical. Strainers. Most traps are equipped with strainers or have integral strainers built in. Many of the trap internals are very small, and pieces of pipe scale or rust could lodge in the trap and cause it to cease to operate. These strainers are designed to keep these small pieces of trash out of the trap. Where strainers are installed, it is important that they be blown down periodically. Industrial sewer system. A plant sewer system collects all drains, water and process fluids from the process units. All water is collected in a series of ditches and routed to the plant waste treatment area. Units that have hydrocarbons that will remain in the liquid phase at ambient temperatures have an American Petroleum Institute (API) separator, which separates the oil phase from the water phase before routing the water to the plant sewer system. Removed oil is rerun or used for fuel. Some plastic units have only a simple system to remove oil and pellets before sending the sewer water to the plant system. The plant sewer collection header runs liquid full all the way to the waste treatment API separator. Running at liquid full prevents any hydrocarbon gases from collecting in the sewer line to form a potential explosion hazard. The effluent water from the API separator flows to the surge basin in the waste treatment area. All contamination in the sewer water is removed in the waste treatment system before the water is returned to surface streams or lakes. Sanitary sewer systems are generally routed to the waste treatment area, where they are treated to remove contaminants. Sewer drains are trapped by a liquid seal in such a way as to prevent gases from backing up into the drain lines. Refrigeration system. Heating and cooling are two important aspects in modern process control. Refrigeration systems such as air conditioning are used to provide cooling to industrial applications. Refrigeration units are composed of a compressor, high-pressure refrigeration gas, a heat exchanger, cooling tower, a receiver, an expansion valve, low-pressure refrigeration liquid, and another heat exchanger, called an evaporator, low-pressure refrigerant gas. In the refrigeration process, low-pressure refrigerant gas is drawn into a compressor, converted into high-pressure refrigeration gas, and pushed into a shell and tube heat exchanger. During the compression process, a tremendous amount of heat is generated and must be removed by the exchanger. During the cooling process, the gas condenses into liquid phase and is collected in a receiver. From the receiver, a high-pressure liquid refrigerant is pushed through a small opening in an expansion valve. As the liquid expands, it changes phase. The boiling point of the refrigerant is so low that a cooling effect occurs in the evaporator. As the low-pressure refrigerant leaves the evaporator, it enters into the suction side of the compressor and the process begins again. One of the most important systems in process units is the refrigeration system. The recovery of ethylene, for example, depends on the efficient operation, reliability, and flexibility of the refrigeration systems employed. Let's review some of the basic principles involved in refrigeration and the equipment utilized. Because heat is transferred from high-temperature areas to low-temperature areas, whenever it is necessary to cool a substance below ambient temperatures, it is necessary to artificially create a lower temperature first. To lower temperatures, process plants use fluids that boil at very low temperatures such as propylene, ethylene, or ammonia, that is, the same principle as the freon in your refrigerator, car, and house air conditioner. Generally, these refrigerants can be kept in the liquid state at room temperature only if they are kept under high pressure because pressure increases the boiling points of all liquids. An exception to this general rule applies to ethylene and lighter compounds, which are so volatile that it is not practical to store them at room temperature as a liquid. Consequently, they are condensed at sub-ambient temperatures. When the pressure on refrigerants is released, however, these liquids boil violently, and their temperatures will drop considerably. Propylene is a good example of such a liquid. Its boiling point at atmospheric pressure is -54 degrees Fahrenheit. Propylene is normally a gas, but using a compressor can liquefy it. In compressing any gas, work is done, and heat is generated in the gas. In compressing propylene, we add heat to the gas and raise its temperature. Raising the temperature allows us to cool the compressed gas with water, and in this manner the propylene is liquefied. At this point, we have a supply of liquid at elevated pressure and at about room temperature. To make it boil, all we have to do is release the pressure under which it is stored since room temperature is far above its atmospheric boiling point. One factor to keep in mind is that everything has heat content, unless it is at absolute zero or -273.1 to 460 degrees Fahrenheit. Air in a room has plenty of heat, that is why we can cool it with our air conditioners. When a pound of propylene boils away, it absorbs about 188 BTU, called latent heat. If we pour a pound of propylene into an open container and watch it boil away, a thermometer inserted into the liquid will read -54 degrees Fahrenheit or -47.77 degrees Celsius. The heat for boiling comes from the container and anything touching the container, including the surrounding air. Moisture in the air will condense and freeze on the container and appear as frost. This is the sequence of events in a simple refrigeration cycle. The cycle starts with the liquid refrigerant under pressure. The liquid flows from the receiver through an expansion control valve where the pressure is decreased and into an evaporator coil, for example, a chiller. Here the refrigerant picks up heat from the material on the other side of the coil. Beyond the evaporator is the compressor, which puts the vapor under pressure and pumps it to the condenser coils. The heat of vaporization and the heat of compression are both removed by the cooling water in the condenser, leaving the refrigerant once again in the liquid state. In the case of an ethylene refrigeration system, owing to ethylene's volatility, propylene refrigerant rather than cooling water is used to condense the compressed ethylene vapors. No matter how complicated the refrigeration system, the ultimate ejection of heat is always directly to air or cooling water. Most large refrigeration systems operate at several levels of temperature and pressure, called stages or steps. Multiple stages are used because the application of several stages increases the efficiency of a refrigeration cycle and results in lower compressor horsepower. There are practical limits to the optimum number of states. Generally, 3 or 4 steps are employed. It is a good design practice, because of safety considerations, to operate the first or lowest stage compressor suction at a positive pressure to establish the minimum operating temperature. The other temperature levels are set by the design of the particular system. Relief and flare systems. Flare systems are used to safely remove excess hydrocarbons from a variety of plant processes. Flare systems are composed of a complex network of pipes and headers connecting to a knockout drum and flare. Governmental laws and regulations require the flare to be located a safe distance from the operating units and populated areas. Flare systems are part of a plant's safety system. Most process units are lined up to safety relief valves that lift when specified pressures are exceeded. These safety valves discharge into the flare header. Unexpected process upsets are dumped to the flare system as a last course of action. A typical flare system includes a flare, a long, narrow pipe mounted vertically, a steam ring mounted at the top of the flare, used to dispense hydrocarbon vapors, an ignition source at the top of the flare, a fan mounted at the base of the flare, used for forced draft operation, a knockout drum with water seal, and a flare header. Relief system. The discharge from all safety valves, pressure relief regulators, and operating vents and blowdown valves in hydrocarbon service are collected in a closed piping system and sent to a flare stack. Steam, air, and nitrogen vapors discharge to the atmosphere. Steam safety valves discharge through tailpipes at a safe distance above grade or above the nearest operating platform. Thermal relief valves are provided to protect against thermal expansion as required in liquid full service. The flare and relief systems are designed in accordance with applicable regulations and practices to protect equipment and personnel against overpressure situations. Many units that process volatile hydrocarbons have two collecting systems, a warm-wet system and a cold-dry system. This separation is made to avoid freezing, with consequent plugging due to ice formation of the wet vapors. Both systems go to their respective knockout drums, where the cold vapors are warmed and then combined and sent to the flare stack. Hot relief system, hot flare. The hot relief system collects liquids and vapors from units that operate above 32 degrees Fahrenheit or 0 degrees Celsius. The flare header branches throughout the plant and terminates in a slope line leading to the flare knockout drum. The knockout drum is a carbon steel vessel that contains a steam coil to vaporize light materials and to warm up heavy materials so they can be pumped to recovery. The pump can be automated to control level but will automatically shut down on low level in the drum. Low and high alarms in the control room are normally provided. Cold relief system, cold flare. The cold relief system collects liquids and vapors below 32 degrees Fahrenheit or 0 degrees Celsius after expansion into the header. It is important for operators to recognize that, although the cold flare system is designed for extremely cold temperatures, there are portions of some connections to the flare that have a higher temperature specification than the cold flare system itself. The various branches throughout the unit terminate in a stainless steel header sloped to drain to the cold flare knockout drum. The cold flare knockout drum is a stainless steel drum containing a heat exchanger that vaporizes the accumulating liquids. The vapor exiting the knockout drum is kept above 32 degrees Fahrenheit or 0 degrees Celsius. Flare systems. Flare seal drum function. A nitrogen purge is maintained on the flare headers to avoid explosive mixtures in the flare lines. Nitrogen and natural gas connections are provided at the end of the header. Normally, the flare system is operated with a water seal in the flare knockout drum. This water seal ensures a positive pressure on the flare when it is necessary to access equipment connected to the flare for any reason. An analyzer continuously monitors the flare at the stack for oxygen. Flare stack and flare pilots. The flare stack provides an elevated location for combustion in the flare tip. Flare stack elevation is selected to limit radiation heat at ground level. The tip is designed to allow smokeless flare operation at low discharge flow rates. Some flare systems are designed to handle only partial system or equipment failures without smoking. The steam flow to the flare is automatically controlled on the basis of the flow rate of gas to the flare. The flare pilots operate on natural gas and air ignited by a flame front generator. Because of the heat radiation from the flare during peak loads, the flame front generator controls are shielded and located away from the base of the flare stack. Entry into the high flare radiation area must be by permit only and must be coordinated with the operations department. Anyone in the area must be in constant radio contact with the control room. Flare stacks are provided to burn vent and waste gas from the units. Normally the waste gases are burned as fuel gas, but at times when a unit upset occurs, large quantities of gas must be disposed of at low pressure to the flare. The flare burners and piping are designed to handle these flows. They must burn the waste gas with a minimum amount of smoke and must be high enough so that the surrounding area and its equipment are not endangered by flame, heat radiation, and fumes. Flare stacks range in height from 200 to 350 feet. A self-supporting flare stack looks like a large perpendicular pipe, usually with graduated size, and has a burner at the top. Some of the smaller stacks have guy wires for protection against high winds. Derricks support many smaller flare stacks. Ground flares are low flares, about 40 feet high, and are used only for purging lines, pumps, and vessels in some areas. They are equipped with blowers to supply air for draft at the burner. Because ground flares are used for purging only, the controls are manual, and the flares are shut down when purging is completed. Steam is piped to the burner tip of the unit flares to disperse and provide draft for burning off the gas without smoking and to protect the burner tips from the heat of the flame. Part of the steam flow to the tip is fixed and cannot be shut off. A manual loading station, which operates control valves in the steam line, remotely controls the remainder. These are adjusted as necessary to eliminate smoke at the flare tip. The flare tips are equipped with pilot burners to ignite the gas as it flows from the tip. These are always burning, but if one goes out, they can be relight from remotely located flame front generators. Air and natural gas are connected to the flame front generator and are admitted in controlled amounts to form a combustible mixture that flows to the pilot burner through a small, 1-inch diameter, igniter line. A sparking device in the mixing chamber ignites the gas-air mixture, and the flame travels through the line to the pilot and lights it. Separate natural gas lines supply the fuel to the pilots. Some flares are provided with seal drums containing water so that flame cannot back into the flare system from the tip. Others depend on some type of flow from the unit to prevent flame from backing into the flare lines. This flow is usually nitrogen introduced into the flare lines through a meter at some prescribed flow rate. Natural gas can be substituted for nitrogen if necessary. All flares have a knockout drum to collect and train liquids. A pump is usually provided to pump the liquid off to tankage. The technician assigned to the area controls this pumping manually. Usually, an alarm will give a warning when there is a high level in the drum. A high level in the knockout drum can subject the flare to slugs of liquid that will be carried out the tip in the event of a gas release. This situation has resulted in the eruption of flaming liquid from the flare and onto the surrounding area. Utility systems are the combinations of equipment that are used to provide a plant with water, fuel, air, nitrogen, electricity, refrigeration, and other substances or processes it needs to operate. In general, utility systems either separate materials into pure or relatively pure products or distribute supplies to the plant's units in usable amounts, store supplies, and remove waste products. Water systems include raw water and fire water systems, boiler feed water treatment systems, cooling water systems, and steam systems. The condensate recovery system of the steam system is separated into clean and suspect condensate sections. Clean condensate is routed to the deaerator. Suspect condensate is collected in a drum, monitored for impurities, and filtered before being sent to the deaerator. The cooling water system is designed for a supply temperature of 90 degrees Fahrenheit or 32.2 degrees Celsius and a maximum return temperature of 120 degrees Fahrenheit or 48.88 degrees Celsius. The cooling water is supplied from the cooling tower to the users by cooling water circulation pumps. Makeup water to the cooling tower is supplied from the raw water system. Filters may be used to remove airborne solids such as dust and sand and contaminants introduced via the cooling tower makeup water such as silt, organic matter, and waterborne organisms. The cooling water chemical feed system consists of a non-chromate-based corrosion inhibitor, a dispersant or anti-scalant, and chlorine for the control of microbiological fouling. Corrosion in equipment is typically associated with oxygen reacting with the metal, so a deaerator is used to remove air, which contains dissolved oxygen, from water. The deaerator heats the water with steam and dissolved oxygen passes out the vent with the steam. In demineralization, raw water is passed through an ion and cation exchange resins. Utility air, UA, and instrument air, IA, are both supplied from centrally located air compressors. Industrial manufacturers purchase natural gas, NG, from suppliers. A high-pressure pipeline generally delivers gas to the plant. Electric power is received from electric supply companies. Relief and flare systems safely remove excess hydrocarbons. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.